Welcome to FMSP Online Revision. This is for OCR FP1 and we're going to be looking at proof by induction. So let's first of all take a look at the specifications. So it says candidates should be able to A. Use the method of mathematical induction to establish a given result. And just note that this is not restricted to the summation of series. So you could have sequences, you could have questions on matrices, or you could have questions on multiples. And then in part B, it says recognise situations where conjecture based on a limited trial followed by inductive proof is a useful strategy, and carry this out in simple cases. For example, to find the nth power of the matrix 1, 1, 0, 1. So what we're going to look at now is we're going to look at some questions, work through these questions and hopefully enable you to get as many marks as possible when you come to doing the exam. So let's look first of all at a question on series, and this is from June 2011. So there are 3 steps that we've got to go through when we do a proof by induction. First of all, we need to establish what we call the basic case. So that I'm going to call step 1, and that means we need to prove that it is true right at the beginning when n equals 1. So if we let n be equal to 1, then we take the left hand side here, then we're only going to be looking at the first term, so that's going to be 1 over 1 times 2, so that's going to be a half. And then when we look on the right hand side, we're going to have 1 over 1 plus 1, which is also equal to a half. So we have now shown that the left hand side is equal to the right hand side, so it's true for n equals 1. We now do step 2, which is often referred to as the inductive step, and this is the bit where we require perhaps the most working. So let us start by saying we assume that it is true for n equals k. Now that means that basically what we're saying, if we write this out in full, is that 1 over 1 times 2 plus 1 over 2 times 3 plus right up to the last term it will be 1 over k times k plus 1, and that is equal to k over k plus 1. So we make that assumption, and what we're then going to try and do is, on the basis that it's true for n equals k, we're going to try and prove that it's true for n equals k plus 1. So that means we're going to look at one extra term. So I'm going to add that extra term onto both sides. So when we add it to the left hand side, we're not just going up to 1 over k upon k plus 1 now. We're going to have this extra term. So everywhere we have a k, we'll replace it by k plus 1. So that will become k plus 1, and k plus 1 will become k plus 2. And if we've added it on to the left, then we need to add it on to the right. So we'll add it on to the right as well. So we haven't sort of changed anything, we're just now looking at the case where n equals k plus 1. And what we will want to try and do now is we will want to try and prove that this expression, these two fractions added together, is going to be the same as this expression, where everywhere we've got a k, we replace it by k plus 1. So in other words, we want to try and show that the right hand side is equal to this. And it's sometimes a good idea to have that written, but you do have to show you're working carefully. So in order to do that, I'm going to take a common denominator of k plus 1 times k plus 2. On the numerator, so this k plus 1 will go in k plus 2 times. And k plus 1 upon k plus 2 will just go in once. Now on the top line we end up with k squared plus 2k plus 1. On the bottom line it's k plus 1 upon k plus 2. Now what we now need to just look at is to see if we can factorise the numerator, and of course we can, because it's k plus 1 all squared. So in fact we have a common denominator on the top and bottom line, and we can divide through by that, and we are left with the expression that we were looking for. So in this particular case we can now say, so it is true for n equals k plus 1. We then come to step 3, which I've written out because it's very important, but it is going to be a similar statement that you need to make at the end of any question on induction, and that is, if the result is true when n equals k, then we have managed to prove that it's true for k plus 1. But of course right at the beginning, in step 1, we proved that it was true for n equals 1, so by mathematical induction it will be true for all values of n greater than or equal to 1. So that completes the proof of a series, and it's just worth sort of stressing that this algebra is very important, that we try and get this done as clearly as possible. In terms of the marks of the question, you do get 1 mark for the basis step, proving that it's true for n equals 1. You get a mark, a method mark, for adding the k plus 1th term on, and you then get another method mark for trying to simplify and add these two fractions. You get an accuracy mark for ending up with k plus 1 over k plus 2, and then you get a mark at the end for putting in your conclusion. So 5 marks in total. So we'll have a quick look at a different sort of question. This time we have sequences rather than series. So if we have a look at this one, so you've got the first term of the sequence, you've got a recurrence relation, u of n plus 1 is equal to 2un minus 1, and we've got to prove the general term that u of n is equal to 2 to the power of n minus 1 plus 1. So we do the same thing as we did in the last question. We'll take step 1. We will show that it's true for n equals 1. So if n equals 1, then we're given the first term is equal to 2. So we then need to look at this general term and show that that is also going to be equal to 2 when n equals 1. So we would end up with u of 1 equals 2 to the 1 minus 1, which is 0, plus 1, and anything to the power of 0 is equal to 1. So it is equal to 2. So it's true for n equals 1. So we then look at the inductive step, step 2. So we again make the assumption that it is true for n equals k. Now that means basically we're going to assume that this general term u of k is equal to 2 to the k minus 1 plus 1. So we're going to assume that that is true, And we're going to look at the next term. So we're going to let n equals k plus 1. Now in this particular case, what you'll need to do is we'll need to use this recurrence relation, because that is the connection between the k plus 1th term and the kth term. So u of k plus 1 will be equal to 2u of k minus 1. But we know from up here we have got an expression for u of k which we've assumed to be true, so I'm going to substitute that in. So instead of having u to the k, I'm going to have 2 to the k minus 1 plus 1. And then we've got a minus 1. So I have replaced u of k by that. Now at this stage, of course, we're just going to use a few rules about indices. So we're multiplying terms, so we're going to add the powers. So we end up with 2 to the power of k plus 2 minus 1, which is plus 1. So this now is true for n equals k plus 1, because you can see that it is exactly the same as this, where you've replaced k by k plus 1. So the algebra a little bit easier in that particular one, but then don't forget that we then have to do step 3, which says, so if the result is true when n equals k, then we have proved that it's true for n equals k plus 1. We also proved that it was true for n equals 1, so by mathematical induction it's true for all values of n greater than or equal to 1. So again, this conclusion statement is important. So 4 marks there. Again, 1 mark for step 1, proving that it's true for n equals 1. You get a method and an accuracy mark here. So a method mark for using the recurrence relation and substituting in u of k, an accuracy mark for getting 2 to the power of k plus 1, and then another mark here in step 3 for your conclusion. And again, that conclusion is dependent on accurate and correct work in step 2. So we will have a look just at one more question, which really looks at the second part of the specification, where we've got to make a conjecture. So January 2010, question 10. So you're given a matrix M. We're asked to find m squared and m cubed. So a little bit of matrix multiplication there. We're then asked to suggest a suitable form for the matrix m to the power of n. And then we've got to use induction to prove our answer to part 2 is correct. So let's have a little look at how we might do that. So m squared, so as I say, matrix multiplication for this first part. So for m squared, we just want to show clearly that we can multiply matrices here. So we end up with 1 plus nothing, which is 1. 1 times 2 plus 2 times 1, which is 4. 0 times 1 plus 1 times 0, which is nothing. And then 0 times 2 plus 1 times 1, which is 1. We then need to work out m cubed. So we're going to take our matrix for m squared and just multiply it by m. And we'll get 1 times 1 plus 2 times 0, which is 1. 1 times 4 plus 2 times 1, which is going to give us a total of 6. 0 times 1 plus 1 times 0, which is nothing. And 0 times 4 plus 1 times 1, which is 1. So we've worked out m squared, we've worked out m cubed. We're now in part 2 asked to make a conjecture about or suggest a suitable form for m to the power of n. So I think at this stage it's just a matter of seeing here that these terms are all the same for both matrices, but this is going to be 2 times 2 and this is going to be 2 times 3. So for m squared it's 2 times 2, for m cubed it's 2 times 3. So hopefully you would think that perhaps m to the power of n might be 1, 2 times n, 0 and 1. So it's important that you make your conjecture there, and then for the third part we're asked to prove it. So let's just take another slide and just see if we can prove that. So step 1, now in step 1 we've effectively done that really, but we'll write it down. We know it's true for n equals 1 since m is equal to 1, and we've got 2 times 1 here because it was 2, 0 and 1. So it's true for n equals 1. Step 2, again the inductive step, we assume that it's true for n equals k. In other words, we're going to make the assumption that m to the power of k is equal to 1, 2k, 0, 1. And we'll now need to multiply that by another value, another matrix m, so that we can work out m to the power of k plus 1. So we'll let n equals k plus 1 to find m to the power of k plus 1, we'll multiply it by a matrix 1, 2, 0, 1. And if you do that, hopefully you will see that we get 1 plus nothing, which is 1, 2k plus 2 here, 0 times 1 and 1 times 0 is nothing, and 1 times 0 times 2k plus 1 times 1 is 1. So in fact we can see that that is equal to 1, 2 lots of k plus 1, so it is exactly the same matrix, just replacing k by k plus 1, and so it is true for n equals k plus 1. And step 3, just as in the other questions, we need the conclusion. So I've written that out there. So in terms of the marks for this question, 4 marks. So again, you're going to get 1 mark for multiplying m of k by m of k plus 1. You're getting an accuracy mark here for multiplying your matrices, and another accuracy mark for getting this term in the top right hand corner of 2 upon k plus 1, and a mark at the end for your conclusion. In terms of that, the first 2 parts, there was 1 mark for making a suitable suggestion for m to the power of n. There was 1 mark for finding m squared and 2 marks for finding m cubed. So just be careful there. So we've looked at 2 or 3 examples on induction. So what I suggest you do is just have a good look through the papers and do as many of these questions as you possibly can. So we'll end here